Computing determinant with induction. So yeah, like there are a lot of ways to compute determinant, right? But in this one specifically, we'll definitely use the other ways, the normal ways of computing determinant, but also induction will be helpful because since there's an n over here, right? We have to compute determinant of n by one, and so yeah, definitely it makes sense that induction will be in use where we will basically try to prove it for like n equals to 1, n equals to 2, and then generalize that, right? So it will definitely be fun, and I hope you will enjoy the solution. So let's proceed. We want to find determinant of this function, right? I mean this expression, right? And let me tell you how this expression is. So basically over here, I have a1 plus k, and then a1 a2 a1 a3 a1 a4. It goes all the way up to a1 an, right? Again, now there's a2 a1 over here. There's a2 plus k. Basically the diagonals have plus k, but otherwise it's just in a pattern, right? Over here it's a2 a3 a2 a4 up to a2 an. Now done for a2. Now a3 a1 a3 a2. In diagonal, like in the main diagonal, we will have a3 plus k, and then a3 a4 up to a3 an. Similarly, we will go for a4 a5. Again, you see the pattern, right? So yeah, that's how this like matrix is made. And so this is a4 square plus k because there are two a4s, right? And this is a4 an. And yeah, it goes in a similar fashion, and up to an a1 an a2 an a3 an a4 an a5, all the way to an square plus k. So you see the idea, right? It's actually just ai as a. It's just the ai as a, right? But in the diagonal, but if it's diagonal element, that's ai square. Yeah, ai as a plus k. If it's diagonal element, sorry, it's ai as a plus k, right? Okay, so you get the idea. Now we need to find the determinant line, right? So it definitely seems big, and then if you just go on doing it manually, I mean, like with the same big determinant, it will be too hard. But what we will try to do is we will first try to see, like, look it for small cases, right? We will first try to look it for small cases, and then from there we will try to make inferences. From there we will try to see what this determinant could be, like from like n equals to 1, from n equals to 2, from n equals to 3. We'll try to see if there's pattern, and if we see pattern, we'll try to prove that pattern using induction. So yeah, induction is basically like usually in the reason we use induction is we sometimes might know the formula or the solution already, and we just want the proof. So that's why induction is helpful. So yeah, we will go with induction. But first of all, let's try for small cases. Let's see what happens for n equals to 1. For n equals to 1, this is just a1 square plus k, just single element, right? So a determinant of single element is just a1 square plus k. So yeah, there's really nothing to do. For n equals to 2, okay, it's determinant of a1 square plus k, a1 a2, a2 a1, a2 square plus k, right? What you can do is, you know how to like take determinant of 2 by 2 matrix, right? So if it's a b c d, determinant is just ad minus bc, right? Okay, so let's do that. A1 square plus k, a2 square plus k, minus a1 square, a2 square. And now this is a1 square, a2 square, plus a1 square k, plus a2 square k, plus k square minus a1 square a2 square. This one cancels out, and if you take k common, this is just a1 square plus a2 square plus k. Okay, we get the determinant for n equals to 2. These two, we cannot really see a pattern right now among n equals to 1 and n equals to 2. There's a little pattern, there's the square in plus k, but other than that, doesn't really seem like there's one, right? Okay, let's go with n equals 3, and then hope that we will see some pattern. It's not like necessary that we will see, but let's just hope that If we see, then that's good. Otherwise, we need to go on exploring other ideas. A2 A1, A2 square plus K, A2 A3. Now again A3 A1, A3 A2, A3 square plus K, right? Okay. So now this is first, but now I guess you know how to expand, right? So in this case, the first element's time it's minor, right? The determinant of its minor, which is this over here. Again, negative of second element, time it's minor. And I guess you guys know how to find minor, right? Like if I want to find minor of the second element, like I just like cancel these elements and then make determinant of the rest of the elements and then find determinant, right? And again, so over here there's plus sign, minus sign, again plus sign. So third element times the determinant of minor. So that's how we do it. So A1 square plus K times determinant of A2 square plus K, A2 A3, A3 A2, A3 square plus K, right? So yeah, and then now there's negative sign, and then A1 A2 times determinant of I just like cancel the row and column in which the A1 A2 lies. So A2 A1, A2 A3, A3 A1, A3 square plus K, right? And then plus A1 A3, right? The last element times determinant of this will be A2 A1. I just cancel the row and column in which A1 A3 lies. So A2 A1, A3 A1, A2 square plus K, A3 A2. So this determinant, right? Now let's try to expand. So it's A1 square plus K. And now notice that we have already found the determinant of this matrix in the 2 by 2 case, right? It's just that 1 and 2 are replaced now by 2 and 3, right? So we know the determinant which is K times A2 square plus A3 square plus K, right? So I'm just using this result over here. This result that we found in the 2 by 2 case. Yeah? Seems like there's already some sort of induction already. Okay, and then A1, A2. Now this is just A1, A2, A3 square plus A1, A2, K minus A1, A2, A3 square. Wow. And then plus A1, A3 times this is A1, A2 square, A3 minus A1. There's some nice cancellations, right? A1, A3, K. So they cancel out. They cancel out. That's nice. Okay, now over here, this is now this is okay. So what I can do is, so now I need to multiply this by both the terms, right? So A1 square times also A1 square times K times A2 square plus A3 square plus K square times A2 square plus A3 square plus K, right? Okay, minus this is A1 A2 square K. This is minus A1 A3 square K. That's nice. Now let's multiply A1 square A2 square. Wow. Okay, wait. A1 square A2 square, or okay, wait. Over here it's A1 square A3 square, right? I'm sorry. Okay. Now this is A1 square A2 square K plus A1 square A3 square K plus A1 square K, right? Plus A2 square K plus A3 square, A2 square K square. I'm sorry, over here it's A1 square, over here it's A1 square K square. I'm sorry, guys. Okay, A3 square K square again plus K cube minus A1 square A2 square K minus A1 square A3 square K. Now A1 square A2 square K cancels out, A1 square A3 square K cancels out. So this is, if I take K square common, A1 square plus A2 square plus A3 square plus k. Okay. Now over here, let me just write it over here and try to see the pattern. So if I just write with a different color now, so we see that this determinant is just k square times a1 square plus a2 square plus a3 square plus k. This one was just k times a1 square plus a2 square plus k. And this one was just a1 square plus k. Now, one thing is clear. There's a1 square plus k, there's a1 square plus a2 square plus k, there's a1 square plus a2 square plus a3 square plus k, right? So we see that if it was up to 4, there would be an expression a1 square plus a2 square plus a3 square plus a4 square plus k. Basically, all these squares plus k, right? And also, you might have noticed that there's also another pattern. Over here, there's k to the power 0, there's k to the power 1, there's k to the power 2. So in n equals to 4, there should be k to the power 3, right? So I can actually guess the expression for n equals to 4. For n equals to 4, the expression would just be, now there would be k cube and then a1 square plus a2 square plus a3 square plus a4 square plus k. This is just a guess. We are not sure. This is just a guess. So now let us say that, like, we assume that this is true, and then let's try to prove it using induction. And if you are able to prove, then we know that it's right, definitely right. And if you are not able to prove, then this might not be true, right? So okay, let's go with induction. And yeah, we know the expression, like if it's n equals to 4, then there's a k cube, right? So if it's n equals to n, for nth, like general like number, there will be k to the power n minus 1, and then a1 square plus a2 square plus a3 square plus a4 square up to a n square plus k. So our determinant for n by n matrix is k to the power n minus 1, a1 square plus a2 square plus a3 square up to an square plus k. So this is our expected determinant for n by 1 matrix, right? Let's try to prove it. So we have already proved it for n equals to 1, for n equals to 2, for n equals to 3, right? So yeah, like to use induction, like we first need to prove it for some base cases, right? Like n equals 1, n equals 2, or something like that. So yeah, that's already proved. Now we will try to use induction, right? Try to use induction. Or if necessary, we can also use strong induction, right? Like yeah, we can use any of that. So let's try to prove this. Like okay, first of all, to use induction, we'll basically try to assume it's true for a k, right? Assume true for like k into k matrix, right? So that means what it means is, so a1 is square plus k, a1 a2 a1 a3 up to a1 ak, a2 a1 a2 square plus k, a2 a3 up to a2 ak, and then a3 a1 a3 a2 a3 square plus k up to a3 ak, right? And then an a1 an a2, right? An a3 up to an square plus k. We'll assume that this is actually true for k into k, right? So yeah, that should be, oh there are two k variables now, so let me make it m. Let me make this as m because there are already two k variables. I'm sorry for that. So m into m. So this is m. Sorry, what m? So yeah, if this is true for m into m, this is now the k to the power m minus 1, a1 square plus a2 square up to a k square. Sorry. Okay, a m square plus k, right? Okay, now let us try to prove let's prove for m plus 1 into m plus 1 matrix. Okay, and if we are able to do this, now if we are able to prove this using the using the assumption that it's true for m into m, what it means is, like, yeah, like if it's true for m into m, it's true for m plus 1 into m plus 1. Like if you're able to prove this, like one in the result that it's true for 1 into 1, it implies that it's true for 2 into 2. And now that it's true for 2 into 2 implies that it's true for 3 into 3. Now that it's true for 3 into 3, it implies that it's true for 4 into 4. It implies that it's true for 5 into 5, 6 into 6, and it goes on. So it implies that like it's true for all integers or all positive integers, positive integers and greater than 1. So for all of them it's true. So that's how induction works. No, so now let's see. Over here, so let me write the matrix. A1 square plus k, A1 A2, A1 A3, all the way up to A1 AM, and then A1 AM plus 1, right? So A2 A1, A2 square plus k, A2 A3, all the way up to A2 AM and A2 AM plus 1. So this is A3 A1, A3 A2, okay, and then A3 square plus k all the way up to A3 AM and A3 AM plus 1. And yeah, there's an AM A1, AM A2, AM A3 all the way up to AM square plus k, AM AM plus 1, and the last one is AM plus 1. A1 AM plus 1, A2 AM plus 1, A3 all the way up to AM plus 1, AM and AM plus 1 square plus k. We want to find determinant, right? So now we want to use induction. Like we want, like the statement that we want to use induction actually means that now we want to use that, like the fact that the results are true for m into m, for m minus 1 and m minus 1. The results are true for the m less than m plus 1, right? We want to use that is true for the lower numbers. And using those, the fact that it's true for lower numbers, if we can prove this for this m plus 1, like m plus 1, like order matrix, then it's true, right? So yeah, you want to make use of fact that like we have already assumed this as true. So we want to use that. So how do you think we can use that? So to use that, I have an idea over here, right? So basically, we know that again, break determinants, right? Let's see if I had a, if I let's say have a plus 1, b plus 2, c plus 3, x, y, z, m, and p. I guess you guys know that we can break this determinant as a, b, c, x, y, z, m, and p plus 1, 2, 3, x, y, z, m, and p. Now, yeah, like this becomes obvious once you see it through the cofactor expansion of this matrix. If you look at through that, like you might find it's obvious because, like, yeah, there's a plus 1 times determinant of like yp minus nz uh, again minus b plus 2 times xp minus mz plus c plus 3 times xm minus ym, right? Now again, just because these are sum, we can actually break this yp minus nz, like plus 1 times yp minus nz minus b times xp minus mz minus 2 times xp minus mz plus c times xm minus ym plus 3 times xm minus ym. So it's become, so I guess you guys see where it comes from, right? This is actually xn minus ym, I'm sorry. Doesn't matter though. So you see it where it comes from, right? And like, yeah, this is actually the determinant of first matrix, this is the determinant of second matrix. So that's how it works. So the idea basically is, like, if any row or any column, if that was just a linear combination of two numbers, like you can actually break it, right? Break it. Like this one has you having the first number and this one having the second number, right? And the rest of them will just be same. So I guess you get the idea. So we will use this fact. And I just showed it true for like 2 by 2, but you can extend this proof for any number, like any just 3 by 3 or 4 by 4 or anything. So yeah, that's how it's helpful. And yeah, we'll use this to make sure that we can take the maximum benefit of the induction. The fact that we have assumed true for numbers less than m plus 1 to make use of that fact, this property of determinant will be helpful for us. So let's see how we can use it. Okay. So now over here, like what I'm going to do is, we know that I can write over here a plus 0, plus 0, plus 0, plus 0, right? Yeah, I guess you can see that, right? So now, yeah, if I use that fact, now over here, this will just be a1 square plus k, a1, a2, sorry, I don't know. I was just trying to break it. a1 square, a1, a2, a1, a3, up to a1 am plus 1, right? And there's other elements too, and like plus, I'm trying to break it. So k, 0, 0, all the way up to all these are zeros, and then a2 a1, a2 square plus k, a2 a3, and then a2 am plus 1. It goes on, yeah. A3 a2 a3 square plus k goes on up to a3 am plus 1, and it goes on similarly in the downside to am plus 1 a1. It's a bit rough now, I'm sorry. Okay. am plus 1 a1, am plus 1 a2, and it goes on up to am plus 1 square plus k, right? Now over here also it's the same. A2 a1, a2 square plus k, a2 a3 goes on up to a2 am, a2 am plus 1, and then a3 a1, a3 a2, a3 square plus k, a3 am, a3 am plus 1. Again, let me write it to the downwards as it will extend this to the downwards as well. am plus 1 a1, am plus 1 a2 goes on up to am plus 1 square plus k. Now over here, notice that the helpfulness of like breaking it like this is, notice that now this matrix over here is a m by m matrix, right? Because this is going from 2 to m plus 1. So from 2 to m plus 1, there are just m numbers. Also, this is going from 2 to m plus 1 in both downward direction as well as in the right direction, right? So like if there were any gaps, like let's say if there was let's say 2 and then there was no 3 and then 4, like we would not have been able to like use it. I mean, like if there's some 3 somewhere, if there's no 3 in the some row, I mean, the thing is, this is exactly in the form that you want, like from a2 to a3 and then a4 a5 up to m plus 1, from a3 and then okay in down also a2 a3 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 a4, right? You get the idea, right? So yeah, the fact that it's in this form, like from a2 to am, helps us use the induction. And now if we use the induction, right, now if we like expand determinant, like for this side, this is just, first of all, you have the k and the determinant of its minor, right? And your determinant of its minor will just be, we know that this is just k to the power m minus 1, and then a2 square plus a3 square up to m plus 1 square plus k, right? This is the determinant, right, for the over here k to the m minus 1, and there it was from 1 to m, but in this case this is from 2 to m plus 1, and you see why that, right? So yeah, so this is just k to the power m times a2 square plus a3 square up to a m plus 1 square plus k, right? Okay, we already have like we already have determinant in the form that we want. And actually, let me just write the result that we are expecting. We are expecting the determinant of this matrix to actually be, okay, so 1 less than m plus 1 is just k to the power m, and a1 square plus a2 square plus a3 square up to am plus 1 square plus k. We're expecting this to be our answer, right? So we already have almost all the expressions, and now there are some more left over here, right, on the other side, of course. And to get this answer, like, we can actually see what we need. We actually need over here the k to the power m times a1 square, right? Because if that's the case, then I can take it by m common, and then we can get the answer. So yeah, I actually know what answer should I get from this determinant, and that's really helpful. So yeah, that's a helpfulness of using induction, right? So yeah, we want to get k to the power m square. Let's just write somewhere over here. K to the power m times a1 square. Okay, so now let's erase this and go on solving. And then let's go on solving. Okay. Now how do you think we should compute determinant? Again, for this one, notice something. Now in the first row, if I just like replace a1 over here with a2, I get a second row, right? Like let's say over here, I mean, just one of the a1. So over here, it's a1 times a1, right? Over here, this is a1 times a1, right? Okay. Now over here, if I replace this first a1 with a2, I get a2 a1. Over here, it's a2 square. Also, there's a plus k. Yeah, there is. And there's a little different. Over here, if I replace a1 with a2, this a2 a3. If I replace a1 with a2, that's a2 am. So yeah, a2 am plus 1. So there's a lot of similarity, right? And we know that like in determinant, like if I'm adding some constant multiples, I guess you guys know this fact that let's say if I have a determinant, let's say a1 a2 b1 b2, and let's say if I do a row operation that the row 2 become row 2 plus 3 times row 1, some constant of the row. Now this will just be a1 a2, and then this will just be b1 plus 3a1 b1 plus 3a2. Even if I do row operations, the determinant remains unchanged. If it had determinant d, this will again have determinant d. You can see why that's the case if you just expand. Let's say if you expand from the bottom, because now if you use the property that I gave you earlier, that you can like basically break this as a sum. So b1, sorry, this is b2. So b2 plus a1 a2 3a1 3a2, right? Now since there are the identical rows, so this should go to 0, right? So this is our d, and that will go to 0. Like if you want to see how there's just 3a1 a2 minus 3a1 a2, so that cancels out. So whenever there is an identical row, so that means a row with that just differs by a multiple. So in that case, the determinant always goes to 0. So this is d plus 0, and that's why they are same. Now the moral of the story over here is you can always perform the row operations. That means, I mean, just this row operation where you can add a multiple of row with other row and still have determinant unchanged. So that's the property of determinant, and we will use this. We will use this now. Let me just erase this. I think I can select. I think there's a lasso select tool that can make my job faster. If there's not, I think there is. I think this is fast. Delete. Yeah, this is definitely fast. Okay. Now, yeah, so I will use that now to find determinant. Now what I will do is over here, what I want to do is, okay, so let me perform the row operation. Which, let me still in the color of a pen. Okay, let me perform the row operation that row, I want to change the color voice. Okay, if I perform the row operation that row 2, let me use the next color, not this one. I'm sorry guys for making the delay. Okay, if I make the row operation that row 2 is just row 2 what I want to do actually. Okay, yeah, row 2. Okay, what I wanted to do is row 2 minus I want to divide row 1 by A1 and then multiply by A2. Right? If I divide row 1 by A1, so all the A1s will be gone from the row 1 and then multiply it by A2 and all A2s will appear. And I want to subtract this expression from row 2. So basically it's just I'm just subtracting a constant multiple of row 1 from row 2, right? So let me do that. And even if I do this, since I'm just like subtracting a constant multiples time a row to another row, determinant will remain unchanged. I've already explained that, right? So yeah, if I use this fact, you will see that some surprising things happen. This will just be A1, 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 A2, A1, A3, all the way up to A1, AM plus 1, right? Okay, I know that there's an expression over here, so we are trying to find it. Don't get confused. Okay, so yeah, now this is, we know that if I do this, now this will just be 0, right? This will just be 0. This will be k. This will be 0, 0. All of them will be 0, right? And this is a3 a1, a3 a2, a3 square plus k, a3 a4, all the way up to a3 am plus 1, and this goes all the way up to am plus 1 an, am plus 1 a2, all the way up to, this goes all the way up to am plus 1 square plus k, right? Okay, now again perform the next row operation, which is the fact that I can also use this again. I perform this row 3 becoming row 3 minus row 1 by a1 into a3. Now I guess you can guess what happens, right? So it will be in the same form, 0 0 k 0 0 0 0, right? Again I perform the next row operation, after that row 4 becoming row 4 minus row 1 by a1 into a4. You can guess what happens, right? So I will perform all of this until row m plus 1 will become row m plus 1 minus row 1 by a1 into am plus 1, right? Now after all these operations, what I will have over here is just a1 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 a2 a1 a3, all the way up to a1 am plus 1, right? And this will just be 0 k 0 0 0 0 0 k 0 0 0 0 0 0 k 0 0 0, and yeah, all the way up to over here also 0 0 0, and the last will be k, right? So now you notice that this is just a upper triangular matrix. This is just triangular matrix, right? So basically what I mean by triangular matrix is all the elements below the main diagonal are 0. And yeah, we know how to find determinant of such matrix, right? If it's a triangular matrix like this one, determinant is just product of the diagonal elements. Determinant is just product of diagonal elements. Again, you can see why that's the case. Like from the cofactor expansion, right? Let's say if you have A, B, C, 0, B, E, 0, 0, F, you can see that if you try to expand it from this column, so first of all, yeah, if you try to expand from this column, you will just have A times determinant of D, E, 0, F, right? And then others are 0, so 0 plus 0. Again, over here also, if you try to expand it from this column, again, D times F, and the rest of them is just 0, right? So you see, like, this is just A times D times F. So this is basically the kind of induction happening. That's what makes it just a product of diagonals element. So now we know that for triangular matrix, determinant is just product of diagonal elements. And yeah, so our determinant is finally easy to find. So now this is just a1 square a1 square times, we know that this is a m plus 1 by m plus 1 matrix, so there are m k's, right? Because one of them is a1 square, so there is m k's, k to the power m. So that's the determinant, just as we expected. We already expected this result, right? So yeah, now the determinant is a1 square plus k to the power m. I can write it over here. Determinant of this matrix is just a1 square plus k to the power m, a1 square plus k to the power m, and now take the k to the power m common and we get our result. So yeah, so now this what happened is when we are assuming it true for m by m matrix, it's automatically true for m plus 1 by m plus 1 matrix. And again, it will be true for m plus 2 by m plus 2 matrix. Again, it goes on. So it's basically true for all like integers greater than 1, right? And so that's why it's true for definitely for any n which is greater than 1. So we have finally proved that we have finally found the determinant and also proved that it's true. We first guessed determinant and then we proved that it's true using induction. We also used a lot of properties of determinant on the way. So yeah, now we are done. So that's why we can finally say that determinant of this matrix is just k to the power n minus 1, a1 square plus a2 square up to uh, a n square plus k, and that's a nice determinant. One of the interesting things is you can see that this determinant is always divisible by k, given that k is not 0, right? And that's an interesting observation. And there are some other ways to solve this, but yeah, this one is nice and easy. There's also a way using eigenvalues or eigenvectors. You can try that as well. You'll get the same answer. So that is it, guys. I hope you enjoyed the solution. First, we check the small cases, found the determinant, guess the determinant, and then use the induction. This was a really good example. So hope you enjoyed the problem. Thanks for watching, and I look forward to seeing you in the upcoming videos too.